Day 17. We are, I think, still on a plane. You're walking to yet another connecting flight. So yesterday we worked on that ticket problem, which is what you might call a constraint problem. You have a list of rules and a model or an input, and you kind of got to figure out whether a model fits your inputs, I guess. Kind of like previous, when you had something like the n-queens problem, or there's something called the Einstein problem. A lot of people probably have encountered it in school. It's that problem where you have, like, there's 5 houses, yellow, blue, red, green, whatever. And one of the houses has like a German person in it. The other one has like a Swedish person, and the German person drinks Coca-Cola, and all these various rules. Like the Coca-Cola drinker is next to the water drinker. And you take all these rules and you try to figure out a model that satisfies all these conditions. What if I put, the first house is a greenhouse? Would the rest of it be correct? And that's kind of what we did here. We had all these columns, which all could be a different field. And we kind of just have to figure out, like, which field belongs to which. A little simpler than the Einstein problem, because with the Einstein problem you have multiple correct answers for several rules. So you kind of have to, like, try a bunch of different conditions, or try a bunch of different configurations, and then keep going through it until you have a fully correct answer. And there's several ways to do that. There's stuff called backtracing. There's, SMT solvers like Z3, where you put in all these constraints. You put in, what your model is kind of supposed to look like, and it goes through and applies all these various theorems, I guess, to figure out, like, the best way to solve this thing. Or you can use a first-order logic language like Prolog that has, like, backtracing functionality. It's interesting. That one did take me a lot of time. I did try to do different solutions that, were a waste of time. I need to stop messing with Z3 and pay more attention to certain things, I guess. But I got through it. I'm not some super programmer that'll show up in the top 100, but I get the job done eventually. All right, day 17. Your flight slowly drifts through the sky. Let's see. Super secret imaging satellite. They want some help debugging it. Let's see. It's based on a set of Conway cubes contained in a pocket dimension. When you hear it's having problems, you can't help but agree to take a look. The pocket dimension contains an infinite 3-dimensional grid. At every integer 3-dimensional coordinate xyz, there exists a single cube which is either active or inactive. Okay. In the initial state of the pocket dimension, almost all cubes start inactive. The only exception to this is a small flat region of cubes, here puzzle input. The cubes in this region start at the specified active or inactive state. the energy source then proceeds to boot up, executing 6 cycles. Each cube only considers its neighbors. Any of the 26 other cubes where any of their coordinates differ by at most 1. 26. That's weird. Okay. Its neighbors include the cube given 1, 2, 3, the cube 2, 2, 2, the cube 0, 2, 3. Where their coordinates differ by at most 1. Okay. During a cycle, all cubes simultaneously change their state according to the following rules. If a cube is active and exactly 2 or 3 of its neighbors are also active, the cube remains active. Otherwise, the cube remains inactive. So this is similar to that seating problem, where depending on neighbors, something became occupied or inoccupied. If a cube is inactive, but exactly 3 of its neighbors are active, the cube becomes active. Otherwise, the cube remains inactive. Okay. Engineers responsible for this experiment would like you to simulate the pocket dimension and determine what the configuration of cubes should be at the end of the 6-cycle boot process. What was it saying? Any of the 26 other cubes, its neighbors are 26? Seems like a lot. Alright, the engineers, even though the pocket dimension is 3-dimensional, its initial state represents a small 2-dimensional slice of it. Okay. Simulating a few cycles from the initial state produces the following configuration, where the results of each cycle is shown layer by layer at each given coordinate z. Okay, so the cube is active and exactly 2 or 3 of its neighbors are also active. The cube remains active, otherwise it becomes inactive. Let's see. So this one was active and it became inactive. Oh no, yeah, it became inactive because only one neighbor here. No, that wouldn't be a neighbor. Because this should be 2 away. Each cube has only ever considered its neighbors. Any of the 26 other cubes where any of their coordinates differ by at most 1. I mean, the distance between this one and this one, it's not 1, it's 2. But I think it's saying the difference of a single dimension. So basically, any, was it 1, 2, 3, 4, 5, 6, 7, 8, 8 on the other side. Okay, so every cube in like all directions went away. I guess if you weren't considering Manhattan distance, if we were just considering regular distance. All right, I think I get this. After the full 6-cycle boot process completes, 112 cubes are left in the active state. Starting with your given initial configuration, simulate 6 cycles. Okay. So let's do... What does our puzzle input look like? Okay, a grid. So we take our grid, start with our test grid and do the parsing first. So we need, let's just do, since we're working with the infinite set, let's just do a list of tuples. These are cubes. Lines, read all lines. This is the Y length, right? Now let's just what am I doing? That should be good enough. Or let's start with parsing through X. And we'll get Y as well. We'll just assume Z is going to be 0 for everything. So cubes. Actually, let's only add active. So our cubes, is that what we're counting at the end? 100 cubes are left in active state. Yeah. So let's not worry about inactive ones. So let's see if lines Y X equals pound, then add an active cube. That's going to be X, Y, 0. All right. See what we get for parsing. We get, where are my cubes? Let's see, 0, 2, 0, which is X0, 2 down, that's active. 1X is 1 across, 0 down, that's active. 1, 2, 2, 1, and 2, 2. Okay, good to go. So we're going to do a, similar to what we did before, we're going to like go through each one and create a new state. So our rules are, we need to consider the neighbors. This is going to be our function that calculates the next state. Next state, and we're going to give it the current state, and it's going to give us back the next state. And inside of here, how am I going to look up I want to be able to look up cubes inside of our list. I might have to make a comparator. But anyway, we're going to say get neighbors, and we're going to pass over the state and a, I don't know, what are we going to say? Target? So how are we going to do that? I guess we can do something like this. You're going to go from -1 to +1. We'll have to skip the zeros when we get here. We'll do this for X, Y, and Z. I guess we only have to worry if all of them are 0, right? Dang. Can I chain things together like this? No, not in this language. All right, so let's see. Our neighbor to test is this. If state contains neighbor okay. So yeah, we're going 1 off in every direction. Oh, this should be... Let's see, target dot item 1 plus X, target dot item 2 plus Y, target dot item 3 plus C. Basically, 1 off from the target. So for calculate next state, we'll say, and this is, every time we have this list of cubes, we're only looking at active ones. Ooh, you know what? I do actually have to look at inactive ones. All cubes simultaneously change their state according to the following rules. If a cube is inactive, but exactly 3 of its neighbors are active, the queue becomes active. Dang, how am I going to do that? Hmm. Or, no, maybe this is okay. Is it? I guess we can throw in another here. Represents active or inactive. You need a Boolean. You need a Boolean. Hmm. Yeah, it seems kind of dumb. If I represented XYZ as a single integer, I'd have to know the dimensions. I feel like this is, if they smack me with like a whole ton of, this grid is like gigantic, then this is going to be extremely slow. Uh, we'll see. Uh, where do I get to set the default value? This is gonna be slow too. Guess I could wrap this in a try block, which is kind of stupid. Maybe I should have turned this into a class since I'm making it so this couple's so complicated. Let's see. Let's test this out real quick. Let's get position all zeros. See what I get. I get a count of 11. One of these is true, which is this guy, so that's good. But what was it saying about 26? Each cube only ever considers its neighbors. Any of the 26 other cubes where any of their coordinates differ by at most 1. "26? What is 3 cubed? 27. So yeah, I should have had 26 here, right? -1 to 1. Oops. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. My... Ooh, oh, I see. I see. Missing equal sign here. There we go. 26 neighbors. Nice. And couple of these are true. 110. 1 over and no. 1 over and 1 down is true. What? Zero and 1 down is true. That's not right. Oh. I messed something up here. Oh. Whoops. Accidentally set all the cubes to active. Okay. 0, 2, 1, 0. Looking good. Neighbors. I have 1 true, which is correct. It's this guy. All right, so next thing we need to solve is get next state. So we say for each cube in state, you know, it'd be nice. Oh, actually, no, that's fine. All right, let's see. Oh, I need to change this to give it an extra field here. All right. Next state equals list. For each cube in state, let's say get neighbors for cube. And what do we do here? Now, yeah, this is the tricky part. Because I need to add the new neighbors that aren't in state. So how about we do this? Let's pass in state as a reference. And if we get to the point where the state doesn't have the neighbor, we'll add it to the state as well. So that should make it so that when we get to the outer edges of our cubes, it should add new neighbors. So get neighbors, ref, state, cube. All right, and if neighbors, we want to count. This should be our active count. And we want, so if cube is active and exactly 2 or 3 of its neighbors are also active. So if count equals okay. Active neighbor count equals this. If cube.item4 is active and active count is greater than or equal to 2 and active count is less than or equal to 3? Is that what I said? Exactly 2 or 3 of its neighbors are also active. Oh, I guess we need to invalidate this. So if this is not true, then cube yeah, we can't set the value. We need how do we... Am I going to be able to do this? I'm not sure if setting new cube to cube, if that's going to pass by reference or pass by value. Else. If the cube is inactive, but exactly 3 of its neighbors are active, the cube becomes active. Cube.item4 equals false, and active count equals 3, then it becomes active. Yeah, I don't want to do this reference by state thing here, now that I think about it. Instead, I'll reference a new state. Okay. There we go. So our next state should contain the new cubes. Ooh, that's complicated. So we'll run it once and see what we get. So cubes now has 203. 203 cubes. I guess. It expands that fast? super slow. Active count is only 3. Oh, that's because I can't do this contains thing anymore. Where am I? No, this is right. I'm only checking each dimension. Let's look at this. How are we supposed to expand? H cube only considers its neighbors, any of the other, so on. Even though the pocket dimension is 3-dimensional, it's 3 by 3 by 1. After one cycle, we only expand by 1 dimension? And why is my active count only 3? It should be much higher. Which ones say true? Ooh, that's hard to check. So get next state for what are we looking at? We're looking at cube, which is 0, 0, 0. Oh. Again, I'm getting caught up with the check. If a cube is active and exactly 2 or 3 of its neighbors are also active, the cube remains active. So it should be, if cube is active and it's not within 2 or 3, then make it false. All right, so cube 0, 1, 0, we're saying that 0, 1, 0, which is this guy right here. We're saying this guy becomes active. No. Zero, 1, 0. Its active neighbor count is 3, which I guess that's true. There's 3 right there. Cube 0, 1, 0. Which should be this guy. During a cycle, all cubes simultaneously change their state according to the following rules. If a cube is inactive, but exactly 3 of its neighbors are active, the cube becomes active. Why did you become active? Not entirely sure. 0, 0, 0 became active? That doesn't make sense. There's only 1 right next to it. All cubes simultaneously change their state. What is... I assume that doesn't mean... Active count is 4. So everything became false. No. Two, 2, 0. Yeah, maybe it's this, maybe it's the fact that I'm doing... I'm making a... passing this new cube as a reference. Can I create a tuple like this? Ooh, nice. Cannot convert from... Why? Okay, how about this? All right. I'll type this out. Zero 1 0 becomes true. Again, that's not right. Okay, so it wasn't this guy's fault. Well, I'm confused about why this flips. Why do you have 26? Yeah, I don't understand why this one flips. Cube is inactive, but exactly 3 of its neighbors are active. Cube becomes active. Each cube only considers its neighbors, any of the other 26 cubes. Yeah, I'm just baffled here. Active count is 1. What for 000, active count is 1, which should just be this guy. I don't see how this would flip. Hmm. This one goes inactive. During a cycle, all cubes simultaneously change their state. Even though the pocket dimension is three-dimensional, initial state represents a small two-dimensional slice of it. Yes. Small flat region of cubes. The cubes in this region start with the specified active or inactive state. Yeah, I'm not understanding these rules at all. This does not match up with what I'm seeing here. This the cube is active and it satisfies these conditions, it goes true, but we're saying if it doesn't satisfy those conditions, it goes false. Which makes sense from what I'm seeing. This guy should only have one neighbor. I don't see how this one would flip. Because it has, you know, what is this, 5 neighbors that are active? Yeah, I'm completely confused. I've no clue what's going on here. If a cube considers its neighbors and there's 26 around it, this is position 0, 0, 0. This is position 0, 2, 0, which is more than 1 away. And it's y dimension. So the only neighbor for 0, 0, 0 is this guy, which is 1, 0, 0. So this guy has 1 active. If a cube is active, no, this guy's not active. If a cube is inactive, but exactly 3 of its neighbors are active, the cube becomes active. Otherwise, it remains inactive. So this guy should remain inactive because it only has 1 neighbor, not 3. But we see here at position 0, 0, 0 that it becomes active for some completely unknown reason. Or maybe, I wonder if this means cycle 1. Let's run this twice, just in case. Oh man, this is super slow. What is it doing? Okay, so it has grown to an insane size. And our active count is 23. This is what? 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's try to run this 12 times. Or what was it, 6 times? And it's going to take forever. I gotta figure out how to speed this up too. I mean, in this, they're showing it after cycle 1, not even, only increasing by 1 in the z dimension. Why wouldn't we increase down here? You know, because this guy, what is it, position 1, 4, or no, 1, 3, 1, 3, 0 would flip. An infinite 3-dimensional grid. Maybe I should make this an integer array. But how do you expand an integer array? you copy it to a list and then array.resize. Completely baffled. Yeah, it's confusing that it's only expanding by one dimension. Or one direction in one dimension. Cycle 2 expands twice. What is this? 1, 2, 3, 4, 5. So 25 times 5. 125. Yeah, shouldn't we only have 125 in the cubes? But we have 203. Why? What is this guy doing here? 130. And these rules don't make sense. I mean, the rules make sense, but the results that they're showing me don't. Mm-hmm. Yeah, I can try changing this list of tuples into a three-dimensional integer array, but that is not going to make these rules make sense. Mm, looks correct. What conditions would we have to pass to get whatever this weird results are? So if we looked at 0, 0, 0, we'd have one neighbor that's active. But for some reason, it becomes active anyway. Dang, I might have to give up on this one. I can't even figure out the rules. I... yeah, I'm just baffled on what it's trying to explain. These rules don't match up with the example. Pushes position 0, 0, 0, which is right here. 3 by 3 by 1. Hmm. Yeah, I don't know. Um, I'm I'm stumped on this one. I can't even figure out the rules to get to the point where I can start solving it. I mean, I am having some issues here where it's extremely slow. I can probably replace this with maybe a dictionary. Hmm. What would I maybe an immutable list. I mean, those are good for inserts in any position. Well, no, I don't really care about where inserts at because I'm only adding to the end of the list. Yeah, listed tuples seems okay. Wonder if there's maybe a faster lookup though. How would I represent the XYZ coordinate as a single integer? Can you have a dictionary? Yeah, I guess you could have a dictionary like this. Is that not valid? No, it's valid. I guess a dictionary should be able to hash a tuple. You know what? Since I'm not getting anywhere, let's go ahead and make this change. I'm probably gonna have to abandon this one and I guess look up an answer, figure out how other people solved it. Because yeah, I'm again for like the 50th time, I'm baffled here. Neighbor, state, new state. So basically the same thing, except cubes. I'm gonna add it like this. Right, and then down here, I'll set a tuple like this, and I'll say if, put this up here, if state contains key of neighbor, then what do we want to do? Then we want to add neighbors, add neighbor, and then whatever the current value is. Oh, why? Oh, you're still a list. Let me help you with that. Where was I? Okay. Else neighbors dot add neighbor and then false. Yeah, a lot cleaner than this. Down here, we need to change this to our dictionary too. Dictionary. Dictionary. Everything's a dictionary. All right, new cube equals When are we getting new cube? Let's see, get neighbors. Get neighbors needs to be a key value pair for a cube. Key value pair of this and this. Target dot key 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 okay. Well, I guess we didn't really need the key value pair, but whatever. Let's see, if cube dot value is true, then new cube dot next state dot add new cube and false. Hmm. Was I not adding the original cube? I'm pretty sure I was. Item with the same key has already been added. Triad. What do we get active count of 4? Cube count of 75, which doesn't seem right. Or maybe it is. What would that be? Um, is there a button for cubed root? I don't know. I don't know what I'm doing. Two, 1, 0 is true. Let's see, 2. No. 2 and then 1. So yeah, that guy should be true. But this guy should stay true, but for some reason it goes inactive. 0, 0, 0 should be still inactive, but this example thinks not. Is this any faster? Can I do 6 iterations now? I can. Oh. It was fast. Because my active count is 54. Definitely not 112. Yep. Completely lost. Now, what would have to be true to turn this to active? As we look at it now, it has 1, 2, 3 neighbors. This guy, and this guy. So it should be active on the next iteration, which I think would be here. Yeah. What do we get after 7 iterations? 109? I don't know why I ran that. Day 17 input file path. I got this guy. Seems to be parsing correctly. Got an efficient data structure. I have a method of calculating the next state. When I run this and debug, I get 26 neighbors. And I get the same count as when I do it manually by just eyeballing it. Yep. I do not understand. Yeah, I mean, I know how I would solve this, but I can't comprehend what these rules mean. Cube is active and exactly 2 or 3 of its neighbors are also active. The cube remains active. But this guy only has 1 neighbor. Well, this is inactive. If a cube is inactive, but exactly 3 of its neighbors are active, the cube becomes active. I don't know why they put a negative in here. If a cube is inactive, but exactly 3 of its neighbors are active. Yeah, I don't know. I'm giving up on this one. I guess I just can't read. So this guy is this guy down here. Or at least it should be. This one has 1, 2, 3, 4 neighbors. This one has 1, 2 neighbors. But down here, it goes inactive. But according to this, it should have stayed active. So yeah. It's frustrating. Yeah, unfortunately, I'll just have to read somebody else's answer because I can't even comprehend what the question is asking me to do. Alright, well, I guess these things happen. That's it for this one. It's not the same center. Oh, I see this in chat. It's not the same centerpiece in the example. Hmm. Yeah. I think I'm gonna kill this one anyway. I'll probably just have to, read other people's comments and kind of figure out what's going on here and solve it from there. But yeah, I don't think I want to spend too much time trying to figure this one out. Hmm. After the full 6 cycles, 112 cubes are left active state, but I have I have 54. Okay. Yeah, I'm gonna end this stream. I'll figure this out after I get some sleep. I'm already flagging. Okay. That's it for this one.